Welcome back, everyone. Today we are going to talk about power analysis. So what is power analysis? Power analysis is a statistical method that we use when we want to determine the sample size that's required in order for us to detect a particular effect size with a particular level of confidence. You can also use it to figure out if you have a fixed sample size, well, what is the maximum or minimum effect size that I would be able to detect in this study? So when do you conduct this? Well, usually when you're planning a study and you want to determine, all right, how many participants do I need to collect data from so that I have a pretty good chance here of being able to actually find a difference between my groups or some sort of a relationship if there really is one. So that is when you want to figure out if you have adequate statistical power. So for example, the Alliant Institutional Research Board asks on their protocol that you have to fill out what number of participants do you plan to enroll in this study, and how did you determine the number of participants that was appropriate for your study? You've got to answer those questions. So why would you conduct a power analysis? Well, if you want to ensure that you've got an adequate sample size, that's one reason. You don't want to do a study that's underpowered and fail to detect meaningful effects, and you don't want to recruit too many people, that is, end up with an overpowered study that's going to waste resources. So when you're planning research, power analysis helps you design studies that effectively balance the statistical rigor, that is having statistical power, with practical feasibility. There's also ethical considerations. Power analysis reduces the risks that you're wasting participants' time or exposing them to interventions that won't have a sufficient benefit, for example, if it's a drug trial. And for your dissertation research, your power analysis is going to answer and help you justify the sample size that you pick, both to your committee and also to the IRB. It adds credibility because you have a justification for why you picked a sample. You're not just pulling it out of you know where. And you will minimize the extent to which you waste resources, because you'll get just the amount that you need and not more, and get it done and get out of this place. So obviously, the other reason you would conduct is you want to ensure adequate statistical power, that you'd actually be able to reject your null hypotheses for your hypotheses if you should. And finally, you want to be able to have an answer for the IRB without just totally guessing, right? So there's your last reason. So there are 4 required components to do a power analysis. If you have 3 of these, you can get the 4th. So it's kind of like algebra. You need power. You need your statistical significance level, or alpha. You need your sample size, and you need to know the effect size or an estimate of the likely effect size. There are some other factors that pop up. So for example, if you're doing ANOVA, the number of levels or groups of the independent variable matters. If you're doing regression, the number of predictors that you use or want to use matters. And if you're doing something with categorical data, so chi-square, the number of categories or cells of those categorical variables matters. So statistical power, what is it? Well, it's your likelihood of detecting a difference or relationship if one truly does exist. So it is your ability to find true positives. Reject the null when you should. So about 80% or higher statistical power is considered conventional. So that's what we go for. So what's that mean? Well, it means that you have an 80% or higher chance of detecting a difference or a relationship if it really does exist. Type 2 error is sort of the flip side of power, because it's defined as beta, and power is 1 minus beta. And a type 2 error means that you have a power of 80% means you have a type 2 error rate of 20%. And what's a type 2 error? That is when you do not detect a difference or relationship that does truly exist. So there is a relationship in your data, and you say, hey, you know what? Based on my stats, I don't see one. That's what we call a false negative. Now, your alpha level, you should be really familiar with this point in time. But just to review, it's your likelihood of making a type 1 error. What's that? Well, that is detecting a difference or relationship that does not truly exist. That's a false positive. So up top, you can see I've got some examples of a type 1 and a type 2 error for you to take a look at. That's Bigfoot, yes. So 0.05 and 0.01 are conventional alpha levels that we accept, just like 0.8 is the conventional statistical power level. So what's 0.05, 0.01 mean? Well, it means that you have a 5 or a 1% chance, depending on 0.05 or 0.01, of detecting a difference or relationship that does not truly exist. That is rejecting the null when you should not. So an alpha of 0.05 is a 5%, an alpha of 0.01 is a 1% chance. The next of the 4 required components for conducting power analysis is sample size. If you don't know what that is by now, you're in deep trouble. It's just the number of participants that are in a study, or small n, sample size, is the number of participants that are in a study group or level of an independent variable. The next one is effect size. So effect size can be defined in different ways. So there are effect size measures. Effect size measures are unstandardized values that quantify the observed effect, relationship, or difference in the study. They are an indication of the magnitude of effect. So some examples of that, well, if you get the mean difference between two groups, just mean 1 minus mean 2, that is an effect size measure. A raw regression coefficient is a effect size measure. The risk difference between two conditions is an effect size measure. So these have limitations. Specifically, they're tied to the unit of measurement. So if it's IQ, they're tied to IQ points. You would get a difference in mean IQ points. And the problem with things that are tied to the unit of measurement is they cannot be easily compared across different studies with different variables or different contexts, because they're specific to that particular measure. So on the other hand, we have these things called effect size indexes. So what effect size indexes are standardized metrics that provide a common scale for reporting the size of an effect from a study. This allows for interpretation and comparison across different field sample sizes and study designs, kind of like z-scores if you think about it. So not all effect size measures are also effect size indexes, but all effect size indexes are the standardized measures, and I'll talk about differences. So what are some examples of effect size indexes? Cohen's D, which I don't think we've run into yet. Cohen's F squared, which I also don't think we've run into yet. Eta squared. Pearson's correlation coefficient, which we've done, is actually an effect size measure and an effect size index, meaning you can compare correlations across studies. Odds ratios, and there's many, many others. So what are the benefits of effect size indexes? Well, they allow you to compare effects across different studies. They allow for interpretation of the relative importance of an effect. So I can compare that this effect is more important than that effect because they are based on the same denominator. And most importantly for this lecture, you can use effect size indexes for performing power analyses, whereas you cannot use effect size measures that are not also effect size indexes. Here's the good news. Well, effect size measures, for the most part, can be converted into effect size indexes, and then you can use them in power analysis. So let's talk about effect size measures for various statistical tests and what effect size indexes they map to. So here's a big table that lists all the different statistical analyses that we cover in the stats courses I teach. The effect size measures that are commonly reported for those studies. And then the final column is the effect size index that can be used for that particular statistical analysis. And in most cases, the effect size measure can be converted to the effect size index, or elements of the effect size, like the means and standard deviations, can be used to calculate an effect size index. So power analysis requires that the effect size metrics that are used be indexed to both sample size and statistical power. Otherwise, so they can do fancy formulas with them. Otherwise, they're not able to do that. And then effect size measures like R squared or multiple R squared or mean differences, mean 1 minus mean 2, can be converted to an effect size index such as Cohen's F or Cohen's D respectively. And again, those measures, Cohen's F and Cohen's D, are indexed and standardized relative to their unexplained variability. So it's kind of like dividing by the standard deviation when you do a z-score. They have a common denominator, and therefore you can compare them about studies. But do note that many of the statistical tests, even though they may have different effect size measures reported, typically they can be combined into common effect size indexes. So this page shows formulas that can be used to convert effect size measures to effect size indexes. And it turns out that many statistical analyses that we cover can be converted to just, in fact, all of them, just 5 common effect size indexes. So there's Cohen's D, which covers the various t-tests and interrupted time series analysis, at least the intervention parameter. And there's Cohen's F, and basically all the ANOVA models can be converted to Cohen's F, so eta squareds, omega squareds, etc., partial eta squareds. Then there's Cohen's F squared, and that particular effect size index covers the regression analyses of various types, whether it be linear, logistic, or survival, which is Cox's proportional hazards regression. Then ones that are kind of on their own are Pearson's R, which you've calculated before. You don't really have to do any converting of that. And another one for all the chi-square tests is called Cohen's W. So let's continue to talk about that final required element for conducting power analysis. And that is the need to have an expected effect size in order for you to determine a minimum required sample size. So to conduct a power analysis, you need an estimate of the effect size that you expect to observe in your study. So if you're doing an experimental study, you might you need an answer to the question, how big do I think the impact is of the independent variable on the dependent variable? For a quasi-experimental study, you need an answer to the question, how much do I think the IV groups differ on this dependent variable? For correlational studies, you need an answer to the question, how strong is the relationship between these variables? For regression, the question is, what percentage of total variability in the dependent variable is predicted by my independent variables or predictors? So what is the expected correlation? What is the expected difference in means? What's the expected R squared, etc.? So for example, what is the expected difference between the dependent variable means between two different independent variable groups? Do I expect them to differ by 5% or 20% or 50%? Another way to think of this is, do I expect them to differ by a small, a medium, or a large amount? So it turns out, and this should be no surprise, based on our prior discussions of power, that larger effect sizes require smaller sample sizes to detect, and the converse is true. Smaller effect sizes require larger sample sizes to detect. So recall the discussion of comparisons of different eggs for birds. On the left there, you've got goose, geese, ducks, and chicken. You can see there isn't a huge difference between those. You need a big sample size of eggs in order to detect an average difference. On the right, you've got, remember the one on the left is an ostrich, and the one on the far right, the teeny tiny one, is a hummingbird. You wouldn't need a big sample size of eggs of those types in order to detect a difference. That is a large difference or a large effect size. So how do you go about estimating what your expected effect size is going to be? Do you just guess? Hopefully not. So the best source is to look at previous research. So you can look in the research literature. You do a literature review as part of your dissertation. Look for meta-analyses in particular. And the goal there is to identify effect sizes from similar prior studies that you could use that effect size as your guess of what you'll find in your study. So, for example, you could look at the effect sizes from prior studies on similar interventions, and then guess, well, if they got a 5% difference or a 2-point difference or whatever it be, that's what I expect to find in my sample using the same questionnaire and methods. Another way to do it, if you can't find a prior study, is to conduct a pilot study, a small-scale study. So use your materials and see what sorts of effect sizes you get based on a teeny tiny sample, or you can at least get estimated means and standard deviations that you can use to create an effect size. So you could, for example, conduct a pilot study of correlation where you have 5 people, just do your questionnaires and you calculate a correlation, and at least you have some guess at what the likely correlation is going to be in your real study. Another thing you could do is look for subject matter expertise. So if there's subject matter experts in your area, you could consult them, and you could say, what's a realistic estimate based on your professional or practical expectations for how big of a difference, how big of a relationship I expect to see in my study based on what I'm doing. So for example, if you're doing a study regarding health, you could talk to a cardiologist and find out that they estimate a moderate improvement in patient outcomes based on their previous clinical experience with similar interventions. So you would say, well, I expect a moderate outcome based on my study of this intervention. The final choice, and the one we're going to talk the most about today, is use conventionally accepted values as your estimate of the expected effect size that you'll see. So find standards in the literature. And one of those standards, for example, is to use the effect size benchmarks from Cohen's 1992 journal article called A Power Primer, and that is in the course materials. So again, Cohen's study or article, A Power Primer from 1992, is a famous study in statistics, and it sort of revolutionized power analysis overall, and it is in the course materials. You definitely want to download this. You're going to need it for your dissertation. So what makes this Cohen study so famous is that it included effect size benchmarks that you can use. So the study provides small, medium, and large benchmark values for each of the effect size indexes. So you could say this is a small value for a Cohen's d, a medium value for a Cohen's d, or a large value for a Cohen's d, and you can use that in your power analysis. So when do you use a small effect? Well, you use that when you only expect a modest difference or weak association in your study. You could use a medium effect size from Cohen's benchmarks when you expect moderate differences between groups or a moderately sized association between your variables. The large one is when you expect big differences or really strong associations. So when you do not have other options, these benchmarks give you a reasonable estimate of the expected effect sizes, and accompanying power analysis tables with minimum sample sizes required to achieve 80% statistical power. This study really does save a lot of people's butts. So let's do a couple examples. So example 1, if you expect a large mean difference in a study that has 2 groups, you would use Cohen's d. So I highlight the study there for Cohen's d. And a large mean difference is a d of 0.8 in your for your power analysis. So another example, if I'm doing correlational studies, highlight that row. If I'm doing correlational studies, and so I've got 2 variables, and I expect a small correlation between those variables. Well, you can see I'm going to use 0.10 in my power analysis as my measure of effect size estimation. And then finally, if I am doing predictions, so I'm doing a regression study, I've got 3 independent variables and I expect a moderate percentage or proportion of variability accounted for in my dependent variable using those 3 independent variables. I would use Cohen's F for a multiple regression, and the effect size I would use is 0.15. So Cohen's benchmarks and sample size tables are part of his article from 1992, and it provides the effect size index minimum sample sizes that are required to have 80% power for a given effect size value. So there's the 2 tables right there with some annotations from me to try to make it a little easier. So on the left, you have the effect size index values, what are a small, medium, and large effect size. And on the right, for different alpha levels, we're going to use 0.05 since that's the convention. You have the required sample size for different statistical analyses in order to have 80% power. So let's go back to example 1, which was expecting a large mean difference. You got 2 groups. So you're going to be doing a t-test, probably an independent samples t-test. You want 80% power. You're going to keep alpha at 0.05. What is the sample size you need for each group? Well, row 1 of the table on the left shows us that the effect size index that we should use is Cohen's d. And among the small, medium, and large effect size benchmark estimates, we are large, so we want 0.8. On the right side, at 0.05 alpha level, we have small, medium, and large effect size choices. We went for large, so if you go to that row, and note that the sample sizes for mean differences are for each group that's in the independent variable. And so in this case, we need 26 per group. So that is a total of 52 total participants for this study of large mean differences to have 80% power, alpha of 0.05, and 26 of that is in each group. How about for a small correlation, 80% power, alpha of 0.05? Well, there's correlation. It's the second row there. And for a small correlation, we use a R of 0.10. So that is our effect size benchmark. On the right, it's also row 2 for significance of R. And this one, it is the total sample size that we need. And again, we're looking at small. So we go to the small column. We need 783 total participants in order to identify a small correlation with 80% power. So crazy. This is why we generally don't go for small effect sizes in studies. They require huge sample sizes. So how about the third example from the prior slide was we're doing multiple regression and we expect moderate level of prediction. On the left, there's your multiple regression row from table 1 in Cohen. And for moderate, we expect a F squared or Cohen's F squared of 0.15. And to have 80% power at alpha of 0.05. Again, note on the table on the right here, there are separate rows for the numbers of dependent variables and multiple R with the sub-row of 3K, where K is the number of independent variables. That's the row that we need. And we expect a moderate effect size, which means overall we need 76 participants per group in order to have 80% power at alpha of 0.05. So that is sort of an overview of how you use Cohen's tables. You can see it's it saves a lot of people's a lot of grief by being able to use them. And that's why this study is so popular. So there are several tools available for conducting power analyses. I just showed you one, that is Cohen's Power Primer. It provides the minimum sample size requirements for 80% statistical power for many basic statistical analyses. The benefit is it's really easy. You just look things up in a table The article again is in the course materials. They can do correlation, most of the t-tests, chi-square, one-way ANOVA, linear regression, some others. If you want to do something with more flexibility, it turns out SPSS also has power analysis as one of its analysis choices under the menu. It is harder to use because you have to actually put in estimated means and standard deviations, for example, to get the effect sizes. It does, however, do all of the above that Cohen does, plus binomial test and some others. There's also the Real Statistics resource pack for Excel, which I use a lot. It is harder again. It's more complex. You got to input mean, standard deviations, sort of the components to make effect sizes rather than just look things up in tables. But it can do all sorts of stuff that the things above it can't, like multivariate analysis of variance, logistic regression, and others. You can do 1- and 2-tailed tests. You have lots of choices. So ChatGPT is another option. It does a pretty good job of calculating effect sizes or minimum required sample sizes for 80% power. For basic analyses, you just have to prompt it correctly. And then there are lots and lots of other free apps and websites that are on the internet. All you got to do is Google the name of your statistical test plus statistical power or statistical power 4, and a bunch of different options will pop up. So this slide presents a summary of the various tools that are available for conducting power analysis, including the ones that were on the prior slide and some others. So here's a big table. You can see the first couple: Cohen's article, SPSS, Real Statistics, ChatGPT we talked about, and then there are some others out there. Most of these are free. So GPower, PS Power, LLM Power, Stat Solutions, and there are various R packages available. R is another statistical programming language. You can see the bottom two can do everything, all the different statistical tests. Whereas LM Powers is pretty limited except for one-way ANOVA, and EpiPower also doesn't do many of the analyses, but it can do epidemiological design, so I wanted to include it in the list. So ChatGPT, Real Statistics are pretty good across the board, but when in doubt, that Cohen article can solve a lot of issues. So just note that the names in the slides are the links that you can actually use to obtain these tools if you'd like to. So that's all you need to know about power analysis. Let's actually do some now. So worked example number 1, what is the minimum sample size required for a forensic psychologist to have 80% power to detect a correlation between impulsivity and criminal behavior among recently released parolees with the alpha level of 0.05. Again, there are 4 required components of power analysis. One is statistical power. We're going to use 0.8 because that's the convention. Significance level, we're going to use 0.05 because that's the convention. So really the two that vary are effect size, which we don't know what the expected correlation coefficient is in this study, and sample size, which, well, that's why we're doing the power analysis. We want it to tell us what is the minimum required sample size we need for whatever the effect size we estimate to be. So to conduct the power analysis, to get that minimum sample size required for our study, we need some sort of reasonable estimate of what the R, our correlation coefficient, we expect in the study to be. So let's say it turns out as part of your literature review, we find that a prior study on impulsivity and criminal behavior among young adult offenders, and they reported a correlation coefficient between those variables of 0.38. We can use that correlation coefficient from the prior study as a reasonable estimate of the expected correlation that we will find in our current study. So that will be our estimated effect size. So keep going with this example. Let's go to Cohen's table 1. We look for a correlation coefficient of 0.38 is it a small, medium, or large effect size? There's our row for correlation. Over there is the columns for the small, medium, and large correlation effect size benchmark values. And again, we're looking at where 0.38 falls. So those are the three values that they give as benchmarks. And where's 0.38? Where it's somewhere between 0.3 and 0.5. So it's somewhere between medium to large. So it's somewhere between medium to large effect size. Because it's not large, we will go with the lowest common denominator here, which is, we're probably going to call it a medium effect size. Because if you can detect a medium effect size, you can detect a large effect size. So the next step here, now that we know that 0.38 is a medium to large correlation effect size, is to use Cohen's table 2 to get the minimum required overall sample size for 80% power to detect a medium to large correlation effect size at alpha of 0.05. So here's Cohen's table 2. That's the one that gives the minimum required sample sizes, and we need to answer the question, what is the minimum required sample size overall to have 80% power to detect a medium to large correlation effect size at alpha of 0.05? There's our row for correlation. There's our tables for alpha of 0.05. Again, they show the minimum sample sizes required for 80% power to detect a small, medium, and large correlation effect size. Boom, there they are. So for large, you need 28. For medium, you need 85. For small, you need 783. So again, we are going with the lowest common denominator here, which is 85. So in order to detect this medium to large estimated effect size, we need at least 85 people in our study to have 80% power. So note how much the required N varies as a function of the effect size. Going from a small correlation requires 783 versus large is only 28 people in your study. Again, this is why we generally don't do studies for small effect sizes. All right, so let's go ahead and do another example of power analysis. In this case, we have a public policy analyst who wants to compare probation violation means between clients who receive community supervision during the pandemic under either a modified or a standard program model. So of the 4 required power analysis components, we know that we're going to use power of 80% or 0.8, 0.05 alpha level. Effect size, yeah, we don't know that. Again, we need an estimated effect size. In this case, it's Cohen's d because we're comparing means, so we'd be doing an independent samples t-test. So we do know the sample sizes, though. They're 70 and 80. However, note that the power analysis requires that the smallest of the samples of the 2 groups meet the minimum required sample size. So it is key in the power analysis. That's 70. So the data for this have already been collected. The pandemic's over. So these sample sizes are fixed. We can't recruit more people during the pandemic. It is what it is. So the question here is, what is the minimum effect size that we can detect with 80% power and an alpha of 0.05 based on 70 and 80 sample sizes in these 2 groups of probationers? So we can conduct the power analysis to determine if the analyst is likely to detect any difference at all, and if so, what size of difference is minimum that they're likely to be able to detect. So here's Cohen's table 2, and the question we want to ask is what is the minimum effect size that N's of 70 and 80 in these 2 groups of probationers can afford 80% power for us to be able to detect. So we're going to use the row in this case for mean difference because we're comparing means. Note, I'll talk about it in a sec. The columns here, we're going to use 0.05 because that is our alpha level, and they show the minimum N per group that is required for 80% power to detect small, medium, and large effect sizes. So a little note at the bottom there, the ones with the red asterisks, the sample sizes that are shown are the sample size that is required for each group or each level of the independent variable. So there are those sample sizes for a large, medium, and small effect. And we've got a maxima or minimum sample size is 70. So the best we're going to be able to detect in this study is a medium effect size. So those sample sizes afford this analyst 80% power to detect a medium minimum effect size difference between the means of the probationer groups. So we can still go on. We can use Cohen's Table 1 to get some idea what is a medium difference in means. And so let's look that up, what the benchmark value is. So here's Cohen's Table 1. We're going backwards this time. Row 1 again is the row for mean comparisons. There's our effect size benchmarks values. So what the D, Cohen's D, is equal to. For a medium effect size, D is equal to 0.50. So what is a D of 0.50? Well, it's like a z-score. So it basically says that value there is about a half standard deviation difference between the means of the groups. So 0.5 standard deviation. So the conclusion here is that the analyst in this doing the study has 80% power to detect a difference in the group means of half a standard deviation or larger. All right, let's do a third example of power analysis. So a doctoral student is planning a study to compare recidivism rates among 3 different probation groups: a standard program, a swift and certain sanction program, and a cognitive behavioral therapy program. What minimum sample size is required per group for 80% power to detect a medium ANOVA effect size with alpha equal to 0.05? So this is ANOVA because there are 3 groups and comparing a continuous dependent variable. So our components, I guess, again, power of 0.8, significance level of 0.05. We know that our effect size is quote unquote medium. So because we have at least a category for that effect size, we can look up an effect size benchmark value. The sample size, what do we need? Well, that's the big question that we want to do the power analysis for. So first, we can use Cohen Table 1 to get the benchmark value for a medium ANOVA effect size. And then we can use Table 2 to get the minimum required sample size per probation group to have 80% power to do this study. So here's Cohen Table 1. The question we want to answer is, what is the value for a medium effect size benchmark? One-way ANOVA is way down there at the bottom, row 7. We're going to look at those columns on the right, which give the small, medium, and large ANOVA, which is Cohen's H effect size benchmarks. We want medium. There are our 3 values. You can see that of the 3 values, a medium is 0.25. And so a medium effect size for this dissertation student study is 0.25, which is it's similar to eta squared. It's approximately 25% of the variability and is accounted for by the ANOVA independent variable. So off to Cohen Table 2. The question now is, what is the minimum required sample size per group to have 80% power to detect this medium ANOVA effect size at alpha of 0.05? Here's our ANOVA row. Note that it's got asterisks and an A on the G. So there are multiple rows here for there are multiple rows for ANOVA that indicate G. G is the number of groups included in the ANOVA. You can see it can cover 2 to 7. The columns show the minimum sample size that's required per group or level of the independent variable to have 80% power to detect small, medium, and large effect sizes. We're looking for medium here. So there are those sample sizes that are required per group. We've got 3 groups, right? So to detect a medium effect size, this student requires 52 participants per group to have 80% power. And note that because it's 52 per group, 52 times 3 is 156. So for the whole study, they need 156 participants in order to complete this. And for a final example of conducting power analysis, we have the situation where a legal researcher plans to use multiple linear regression based on 100 adults, somehow they got, and they want to predict public support for a new policy, and they want to use predictors such as income, sex, education, political ideology, etc., to predict this public support. It's noted that similar models of public support that they've calculated in the past have typically predicted about 20% of the variability in public support. So of our 4 power analysis components, we've got 0.8 and 0.05. The R squared that we would estimate, that is percentage of variability that is accounted for, is 0.2, which is 20%. Note that this is an effect size measure, and in order to do the power analysis, we need to convert it to an effect size index. Sample size is fixed for this, right? There's 100 participants. So the question that we want to answer is, what is the maximum number of predictors, or IVs, they're sometimes called, that this researcher can include in the regression model if they have 100 participants, an expected R squared of 0.20, and they want to maintain 80% power and alpha of 0.05. We can use Cohen's table 1 to convert the R squared effect size measure to the F squared effect size index. The formula is shown there. And then we can use table 2 to determine the maximum number of predictors that are supported by that effect size index value and by a sample size of 100. So off to Cohen's table 1. Question here is, an R squared of 0.2 is that a small, medium, or large Cohen's F squared effect size index? So in row 8, we have this formula that we can use to convert R squared to Cohen's F squared, which the effect size index. There's that formula. And if you plug in the numbers, 0.2 R squared is the equivalent of a 0.25 Cohen's F squared. Now looking at the effect size columns over there for a small, medium, and large Cohen's F squared benchmark values, we can see it's 0.35 for large, 0.15 for medium, and 0.02 for small. And an F squared of 0.25, that's what our R squared was equivalent to, is somewhere between medium and large, about halfway, right? So it's a medium to large effect size. Is what we would call an R squared of 0.2. So next, we're going to use Cohen's table 2 to get the maximum number of predictors that the researcher can include based on a sample size of 100 and this medium to large F squared effect size. What's supported? What do those support with maintaining 80% power and alpha of 0.05? So off to Cohen's table 2, and this is the one that has the sample sizes. The question here is, how many predictors do a sample size of 100 and a medium to large Cohen's F squared effect size index support maintain 80% power and an alpha level of 0.05? So the rows for multiple correlation and multiple regression are down there. They note there's multiple rows depending on K. K is the number of independent variables or predictors that are in the model. The columns show for alpha of 0.05, the minimum overall sample size for 80% power to be able to detect small, medium, and large F squareds for anywhere from 2 to 8 numbers of independent variables or predictors. There's those rows. So again, K stands for the number of independent variables or predictors in the model. And we want to know how many predictors we can support with this sample size and effect size. So there's all the numbers. So over there you can see the sample sizes required for this effect size for 2 to 8 goes from 67 to 107. We have 107 participants, so we're right there between 6 to 7 independent variables. So what's the conclusion? Well, this researcher can support somewhere between 6 and 7 predictors in their multiple regression model based on a sample size of 100 and that R squared of 0.20, which was the equivalent of an F squared of 0.25, and still maintain 80% power and alpha level of 0.05. So hope you learned something about power analysis today, and remember it when it comes time for your dissertation.